Hello and welcome to this OCR A video on Boltzmann distributions, this same squarely at year 12, looking at the energetics chapter, chapter 10, rates. So, what is a Boltzmann distribution? Well, a Boltzmann distribution is describing the energies of molecules in a system. And we draw it on an axis like this, where energy is on X and number of molecules is on the Y. I guess that's number of molecules at a given energy. Now, we start the curve at the origin. The reason for that is at 0 energy, 0 Kelvin, there's not a probability of finding a molecule there. No molecule has been recorded at 0 Kelvin. It's, as far as we're aware, not possible. So, we start at the origin, we come up, we show a bulge, and we come down. But we do not touch the x-axis again. So, 3 things to remember. There's my drawn Boltzmann distribution showing a nice average of particles in that midpoint. And there's 3 things to bear in mind. Number 1 is to start at the origin, as I mentioned. These are kind of the checkpoints, origin. These are sort of checkpoints that the exam board wants to see. Number 2 is that your curve does not hit the x-axis on the right hand side. Yeah? So as we move over here, we don't touch the x-axis. Reason for that is we can have molecules at very high, almost infinite energies. There is a probability of it. If the curve's not touching the x-axis, it shows there's a possibility that an atom could be there. Then the third thing is just to make sure that we have a nice bulge at average energy. So this bit here, obviously, and this really is a probability diagram. The most probability, the greatest area under the curve is in that kind of average energy of the system. So what we can now look at, now we know how to draw a Boltzmann distribution, is look at a Boltzmann distribution at 2 temperatures. So again, I write number of particles, or molecules, on Y and energy on X. And I'll draw in a copy of that first curve we've looked at. And if I call this T1, the temperature that I'm starting with. Now, the question might say something like, what happens at a higher temperature? Draw the effect on the Boltzmann distribution. And what you need to do at higher temperature, there's going to be a broader range of energies that the average molecule exists in, this kind of midpoint of the bulge we've spoken about. And we also, because we're going to widen it and make it broader, we also need to bring down the level of the peak. So we draw at higher temperature something like that, and I could call that T2. Now, if I draw an activation energy on this curve, so if I say at this point, call that EA, activation energy, at this point, everything from the right hand side has sufficient energy in a collision to overcome the activation energy and form products. What we can see is, in our T1, which was at lower temperature, then, so I can put up here just to summarise, T1 is less than T2. Here is the proportion of particles with sufficient energy to overcome the activation energy. But by increasing the temperature, I bring in all of this zone in which particles can react. It's a greater probability, a higher percentage of the particles have sufficient energy to overcome the activation energy due to more frequent successful collisions between particles of higher energy. So using a Boltzmann distribution now, we can explain why at higher temperature there's a faster rate of reaction. A greater percentage of particles have the ability to overcome the activation energy. What we can also look at is the effect of a catalyst on a Boltzmann distribution. So if I just draw another distribution here, obviously again, energy on X, I'm just going to put NO of molecules on Y, and then again I'm going to show my activation energy. If you saw my last video, you'll have seen the effects of catalysts and the different types of catalysis that we can have. So there is my proportion, just like in the last one, of molecules that can overcome this activation energy. If I add a catalyst to the system, we know from our definition of catalysis that catalyst lowers the activation energy. So I can move my activation energy to the left, further in lower energy. I could call that EA cat to show it's the catalyzed activation energy. And what we can see is now all that extra area in which the molecules can react. There's a greater probability of them reacting. So this is another way to look at how a catalyst actually increases rate of reaction by providing a lower, an alternative pathway of lower activation energy, and therefore a greater percentage of molecules can react. That shows it really vividly. So that's the Boltzmann distributions. That's what you could need to know for an exam. Hope this helps. I'll see you in the next video. Like, comment and subscribe. We'll see you then.